Into the fire on Christmas Eve 2024. While most of the world celebrated under glowing lights and winter skies, another story was unfolding, far away from Earth. High above our atmosphere, beyond the reach of human eyes, a spacecraft no larger than a family car was hurtling through the blackness of space. It wasn't just moving fast. It was racing faster than anything humans had ever created, an astonishing 430,000 miles per hour. This small craft carried a big name. It was NASA's Parker Solar Probe. And it was on a mission no spacecraft had ever dared before. Parker wasn't content with orbiting safely. It was plunging inward, closer and closer to the Sun. At its nearest point, it would come within just 3.8 to 8 million miles of the solar surface. That may sound far. But on the scale of our star, it meant entering the corona itself, the Sun's outer atmosphere. For the very first time in human history, we were no longer gazing at the Sun from a distance. We were inside it. And what Parker saw there was both breathtaking and unsettling. With the help of artificial intelligence, scientists began decoding the probe's last and most daring images. What they uncovered defied our expectations. Massive eruptions, colliding like avalanches of fire. Magnetic structures spiraling in graceful, deadly dances. Switchbacks, sudden whiplash reversals, twisting the solar wind into bizarre shapes. Each finding forced scientists to rethink what we thought we knew about the Sun. And each discovery hinted at dangers that could one day strike Earth. High-voltage cannibal CMEs. Among the most dramatic events Parker witnessed were three enormous coronal mass ejections, CMEs, blasting off from the Sun within mere hours of each other. Usually, from Earth, we see CMEs long after they've erupted. But Parker was there at their birth. And from its unique vantage point, something extraordinary was revealed. The three CMEs didn't just drift outward into space. They collided. They merged. They fused into one monstrous eruption. Scientists call this phenomenon a cannibal CME, a titanic surge of plasma and magnetic energy, far greater than the sum of its parts. The sheer scale was staggering. If such a storm aligned with Earth's orbit, the results could be catastrophic. Satellites, power grids, and global communications could all be at risk. Milky Way, the heliospheric current sheet. But Parker's discoveries did not stop there. In the far corner of its imagery, the AI recognized something just as important, the heliospheric current sheet. This is the vast, spiraling boundary where the Sun's magnetic field flips from north to south. Imagine a ballerina's skirt, spinning endlessly, stretched billions of miles through the solar system. For decades, scientists believed it to be a relatively stable feature. But Parker showed otherwise. The current sheet near the Sun was not calm. It was dynamic. Chaotic. It shifted and reformed constantly, reshaping the path of the solar wind. And when a CME lines up with this spiraling boundary, the energy can be funneled directly toward Earth. The difference could mean nothing more than bright auroras, or a planet-wide technological disaster. Crossed arrows switchbacks. Back in 2018, Parker had already uncovered something strange, sharp zigzags in the solar wind. Scientists named them switchbacks. At first, they were thought to be random turbulence. Just noise in the flow. But during this latest flyby, the AI found something unsettling. The switchbacks weren't random at all. They clustered together. They formed repeating patterns, almost like hidden rhythms in the solar wind. Even more startling, some of these patterns matched the timing of CMEs Parker had observed. This suggested a deep connection between the two. Switchbacks might hold the answer to one of the Sun's greatest mysteries. Why the corona, the Sun's outer atmosphere, is hundreds of times hotter than its visible surface. If these magnetic whiplashes act as energy channels, they may be pumping heat into the corona at astonishing rates. But they could also be amplifying the power of CMEs, turning ordinary eruptions into storms of unimaginable force. Ringed planet. The path to the Sun. Reaching this position was no simple task. Parker's daring approach was only possible thanks to a series of gravity assists from Venus. Each flyby slingshotted the spacecraft closer to the Sun. Each one sent it racing faster than any spacecraft before it. On this final pass, Parker's heat shield endured temperatures of over 2,600 degrees Fahrenheit, 1,400 degrees Celsius. Its instruments were battered by radiation strong enough to fry most satellites instantly. But Parker endured. And it sent back more data than anyone expected. So much data, in fact, that only artificial intelligence could process it before the probe's next encounter. Thanks to this partnership between human researchers and AI, faint hidden patterns were revealed. Turbulence in the current sheet. The synchronized waves of switchbacks. Signs of order in what once seemed like chaos. And hints that Parker's greatest discoveries still lay ahead. At this point in its journey, Parker had already transformed our view of the Sun. But the most astonishing, and the most disturbing, the Sun's hidden heart among the many surprises buried in Parker's data, one stood out as completely unexpected. Broom, the cosmic broom. The AI detected a massive region in the solar wind where particle density plummeted almost to zero. A clean, sharp corridor stretching millions of miles through space. Scientists had long known the solar wind was uneven. But never anything like this. The data suggested that one of the cannibal CMEs had acted like a cosmic broom. It had swept particles aside, leaving behind a vast vacuum-like pathway. Visually stunning. But deeply troubling. If such a low-density corridor ever intersected Earth's magnetic shield, it could temporarily weaken our defenses. That would leave us vulnerable to cosmic rays and high-energy particles from the Sun. For the first time, Parker's mission was not just about science. It was about planetary defense. Red Heart, the magnetic heartbeat. Then came another revelation. Parker's instruments detected subtle, faint oscillations in the Sun's magnetic field. For years, human analysts dismissed them as background noise. But the AI found something extraordinary. They weren't random. They formed a repeating pattern. A slow, steady rhythm pulsing every 142 minutes. A magnetic heartbeat of the Sun itself. And it appeared across multiple data streams, magnetic readings, particle flows, even fluctuations in ultraviolet light. The implication was staggering. There might be a global process deep inside the Sun, modulating its outer layers in rhythm. Some scientists now believe this heartbeat could be linked to the mysterious solar cycles, the very processes that drive sunspots, CMEs, and solar storms. If true, it could become a predictive tool. A way to foresee dangerous solar events before they erupt. But one question lingers. Why are we only hearing this heartbeat now, so close to the Sun itself? A solar storm like no other. One of Parker's final and most dramatic discoveries was a colossal filament of plasma. It stretched nearly 2 million kilometers across the Sun. A structure of unimaginable scale. Normally, such filaments collapse harmlessly, raining energy back onto the solar surface. But this one was unstable. Its magnetic anchors were weakening. If it erupts, it could launch a CME far stronger than any we've recorded in modern times. Perhaps even greater than the legendary Carrington event of 1859. That storm set telegraph wires ablaze. And painted auroras in skies as far south as the Caribbean. But in today's hyperconnected world, the damage would be far worse. Satellites could fail. GPS systems could collapse. Electrical grids might go dark for weeks or even months. Such a storm could shake the very foundations of modern civilization. Satellite dished the mysterious signal, and then, Parker uncovered one final puzzle. Not in images, but in radio data. Buried in the probe's telemetry was a repeating narrowband signal. It was structured. It was patterned. And it was coming from Parker's immediate environment. Not the Sun. Not the instruments. But the very space around the probe. Some scientists think it was a natural plasma resonance. Others wonder if it was something stranger. Whatever it was, it defies simple explanation. and it remains one of Parker's greatest mysteries. Sun: The Legacy of Parker. The Parker Solar Probe was designed to answer ancient questions. Where does the solar wind begin? Why is the corona so hot? What forces create the storms that cross millions of miles to touch Earth? It was never meant to return home. It was a one-way journey into the most hostile environment a spacecraft has ever faced. But what it revealed before vanishing into the sun's embrace was more than data. It was revelation. Cannibal CMEs merging into colossal storms. A magnetic heartbeat pulsing from the sun's hidden depths. Switchbacks shaping the very heat of the corona. A plasma filament poised like a coiled serpent. And a mysterious signal that lies beyond our current understanding. Together, these discoveries shattered the idea of the sun as a stable, predictable star. Instead, Parker revealed it as a living, restless engine, capable of both wonder and destruction. Its journey has ended. But the knowledge it left behind will echo for decades to come. It didn't just bring us closer to the sun. It brought us closer to the truth. That our survival as a technological civilization may one day depend on how well we can read our star's moods. And how quickly we can act when it changes. That,